In this poster presentation, I would like to share our first experience with achieving end-to-end network visibility by extending the support for in-band network telemetry to the end hosts. In particular, I will present our Host-INT solution. This work has been done by Carmelo Cascone and myself. The in-band network telemetry greatly improves network monitoring, allowing network operators to inspect individual flows, promptly detecting anomalies and pinpointing their causes. At ONF, we have been leveraging the INT standard to facilitate network troubleshooting and validate SLAs for the Ether platform. The Ether platform is composed of three elements basically. Radio-based stations providing LTE or 5G access to the connected devices, one or more servers running Kubernetes and hosting edge applications which offered services to end users, and a P4 programmable fabric implementing a so-called switch-INT. The switch-INT is used by us to collect fine-grained telemetry information about all the packets traversing the fabric, including alerts when a packet is dropped due to a specific reason. However, observing packets as they travel through switches is knowing only half of the story. For instance, a mobile user traffic can be dropped by the firewall rule configured on a server, but having only information provided by switch-INT, we are not able to detect this misconfiguration. Therefore, there is a need for extending the INT support to collect telemetry information not only from the switches, but also from the hosts, so that with the help of Host-INT, we are able to achieve an end-to-end network visibility for the Ether platform. However, the Host-INT implementation is a bit of challenge due to the specific and complex nature of the network architecture that we have. First of all, the servers typically run Kubernetes to manage edge applications and provide network connectivity between so-called pods. The Kubernetes networking introduces an additional complexity here. Each Kubernetes node may redirect a packet to a different node, load balance the traffic, and perform the NAT function that translates IP addresses and likely the UDP or TCP ports of a packet. Moreover, the INT implementation has to deal with heterogeneous overlay techniques. On the one hand, the mobile traffic is encapsulated into the GTP protocol, and on the other hand, the Kubernetes might use different overlay protocols to redirect traffic between nodes. All of these factors causes a complex forwarding scenario in which packets are encapsulated using different tunneling protocols for different portions of the path. They travel through end hosts multiple times because of redirects, and they are also transformed using NAT in the middle of the path. So many things can go wrong in such a scenario, and that's why we need the Host-INT solution to have a visibility into the network flows and to detect anomalies end-to-end. We decided to implement the Host-INT prototype using the eBPF technology, which allows us to quickly extend the end-host stack without the need for extending the Linux kernel or modifying the Kubernetes network plugins. The picture shows two network interfaces and the simplified view on the host network stack, where the Kubernetes data path can be either implemented based on IP tables or eBPF. The eBPF provides us two so-called hooks where an eBPF program can be attached to. We implement two eBPF programs, one for the ingress hook and one for the egress hook. The egress program sends a per-packet data plane report to the user space using the BPF-perf event array. And in the user space, we implement another component called INT host reporter that listens to the events from the data plane, generates INT reports based on the received information, and streams the INT reports to the INT collector. The Host-INT prototype implements an INT-aware data path on each of Kubernetes nodes. We designed the Host-INT to be independent of the Kubernetes network plugin being used, and so far we have tested Host-INT with two Kubernetes CNIs, Calico and Cilium. We have measured the overhead of the additional Host-INT programs on the path using the netperf, and unfortunately the enhanced visibility comes at the cost of reduced performance. We observe about 5 to 7% lower TCP throughput and transaction rate when the Host-INT extension was enabled. Finally, the work on Host-INT is still in progress, and we met a fundamental problem that hinders the ability to achieve the end-to-end network visibility. The problem is caused by NAT being performed by some CNIs in the middle of the packet path. This leads to a situation in which packets of the same end-to-end flow are reported to the INT collector using different IP addresses and ports. This causes INT collectors to detect two independent flows instead of one, and this breaks the ability to detect anomalies, while also making it hard to visualize and debug end-to-end flows. The INT specification does not provide a clear solution to the NAT problem. We believe that the job of correlating packets before and after NAT should be left to the INT collector, while the INT nodes should provide enough information to make this correlation feasible. In the paper, we proposed changes to the INT specification to enable collectors to correlate packets before and after NAT. We are currently considering two solutions. The first one is to use a domain-specific extension of the INT header to carry an unique flow identifier or the whole pre-NAT information. Or we can have the Host-INT node send the NAT information out of band to the INT collector, for instance using a special INT report or a completely different protocol. We are currently investigating these two alternatives. What's important, our Host-INT implementation is available online and we encourage you to give it a try. As the next step, we are going to improve performance, test Host-INT with more Kubernetes network plugins, and finally deal with the NAT problem. At the end, I would like to dispel concerns about why do we present an eBPF-based solution on the P4 conference. We do this because the INT standard is hosted by the P4 community, and we believe that the Host-INT is needed and relevant work, even if it's implemented without.
I was wondering just what type of int reports do you support right now?
Yeah, so there are three of them in the INT specification. The flow report, which basically gives you information of the packet. The drop report, which is which points the packet that has been dropped, and the queue report. So we support the first two, flow report and drop report. The queue report is kind of hard to implement on using the eBPF. We don't have control over the traffic manager in Linux. And for the drop report, we do support it, but without a specific reason, because we don't have full control over the CNI. So we cannot find a specific reason of packet being dropped.
Okay, I see. Thank you again. Very interesting work.
Yep, thank you.
See you soon. Bye bye.